Hey Chem Kids, Mr. C here. We are back for day 2 of thermodynamics. A little vocabulary before we begin. For the rest of the unit, we are looking at what we call thermochemistry. And this is all about the study of how energy changes within a chemical reactant. So how energy goes from reactants to products, or how we need energy to be put in order to turn those into products. And when we look at energy changes, we're looking at 3 forms of energy. We're going to look at enthalpy, entropy, and then Gibbs free energy. So today, in this video at least, we're looking at enthalpy and entropy. And then later, we're going to be looking at Gibbs free energy, which sort of combines those two into like one kind of neat form of energy that sort of tells us a lot about the system, more than just one of these on their own could tell us about it. So without further ado, let's look at enthalpy. And enthalpy at its heart is the total heat content of a system. So it's how much energy we have within the system. We're usually talking about the energy that's being stored within bonds. And, looking at energy that our molecules actually have. So how much energy do we have in our reactants, and then also how much energy do we have in our products, because it's going to differ for every reactant and every product that we have, and because of that, it differs for every reaction that we have. And for the purpose of this class, we're really interested not in individual enthalpies, but in the change in enthalpy, or in this case, that delta H. So we're back to that delta H, which means change in. It's just now, rather than looking at a change in temperature, we're looking at a change in energy changes here. So we're looking at our product energy minus our reactant energy, and how it changes as we go from product to reactant. When we measure delta H, the way that we measure it, there are standard conditions because it can change temperature and pressure and things get weird, but we measure it at 1 atmosphere pressure and 25 degrees Celsius. So anytime we talk about delta H in this class, it's always sort of at these standard temperatures and standard pressures. So whenever we use those values, we're using values that were defined at a standard temperature. We're saying these bonds have this amount of energy in them. Whenever we look at a reaction, it always starts off, we can sort of plot off the energy if we want to. They always start off with our reactants. Oops, too fast, Mr. C. We always start off with our reactants. This hump is sort of where the actual reaction is occurring. You don't really need to know much about it yet, but that's where the reaction is occurring. And then we end up with the energy of our product. So what we need to know now is we start with reactants, and we end up later on with products. Anytime our reactants have more energy than our products, so the reactants are higher up than our products are, so like in this case here, our reactants are higher than our products, we would go ahead and call that an exothermic reaction. And all that means is that we're giving off energy in the form of heat. So we're releasing energy as we go from reactants to products. So the reactants sort of mix together, they react together, the reaction occurs, and as they become products, we're shedding off that energy. We're giving it out to our surrounding. And because of that, because we're shedding off or bleeding off that energy, we say that the temperature of our system rises. So anytime the reaction gets hotter, we would go ahead and call that an exothermic reaction. So think of like hand warmers or exothermic reactions because they get hotter. We also say that delta H is going to be negative for any exothermic reaction. Another way we can write this or say this, because heat is a product, heat is a product because it's released. So because we're giving it off, we end up with heat. Anything we end up with is considered a product. On the other hand, if our reactant energy is lower than the product energy, we're going to go ahead and call that an endothermic reaction. So if we end with more energy than what we start with, it's an endothermic. And what this means is that we need to absorb energy or heat in order to make this reaction happen. So our reactants have to soak up energy and then they become products. And because of that, the products are higher up than the reactants are. Whenever we look at the temperature, what this means is that the surrounding temperature actually goes down. So this is very similar to like those instant ice packs. Anytime you squeeze one of those, an endothermic reaction happens. It sucks energy in, and it gets nice and cold, and it helps, if you hurt your knee or if you need an ice pack, you can use it for that. Delta H for an endothermic reaction is going to be a positive value. Because energy is absorbed, that means we have to start off with that energy. So we would go ahead and call it a reactant because we are starting with it. And anytime we start with something, that's always going to be considered a reactant. So these aren't in your notes packet, but which ones are endothermic, which ones are exothermic? Well, this first one, because it has a negative delta H, we're going to go ahead and say it's exothermic. The next one is a positive delta H, so because it's a positive number, it's going to be endothermic. The same can be said for number 3, because it's positive, it's also going to be endothermic. And then our last one, delta H, is negative, so we would say it's releasing energy, so we would say this is an exothermic. So how do we calculate it out? This is sort of like the gist, or the big part of delta H. So first we need to balance our chemical reaction. After we balance it, we need to consult our table of delta H. This is in your packets on problems. It'll be given to you, on the test it'll be given to you, but you're going to consult the delta H for each of our reactants and products. And we're going to look it up and just see what those values are, because we will need those whenever we're calculating out our delta H there. Next, we're going to take the number of moles and multiply it by its delta H value for all the reactants and products. So like the number of moles, that's just the coefficient in our balanced chemical equation. So like if we had 2 H2O, we would take 2 times the delta H of H2O. Last, we add together all the reactants. We add together all the products. And then we're going to take our products minus our reactants. So we're going to take what we got in step 5 minus what we got in step 4. Be sure to be careful about your signs here. Positives and negatives do matter, and you don't want to flip it up. Because of that, while you can do this with a phone calculator, it's a whole lot easier if you're doing it with a real calculator, because it's just easier to type in negative signs and minuses that way. So let's look at this example. We have 2 NaOH plus H2SO4 goes to Na2SO4 plus 2 H2O. So our first step is we got to look up and see what the delta H value is for all of our reactants and products. So for our reactants, we have NaOH. And if we look up on our table in the packet, we will see that NaOH has a value of minus 470. Next, we come across H2SO4. Sorry about that. Can't talk today. But whenever we look up H2SO4 on here, we see that it has a value of minus 814. That's all of our reactants. So now we're going to look at our products. We have Na2SO4, and if we find Na2SO4 on here, we see it has a delta H of minus 1,387. And then for H2O, when we look that up, it has a value of minus 286, I believe. Yes, minus 286. So we've looked up all of our values. Now we have to multiply those values by the coefficient. So for NaOH, we multiplied that by 2 because the NaOH has a 2 in it. So we'll take that minus 470 times 2, and we get minus 940. H2SO4 has a coefficient 1, so we just multiply that by 1. So we still have minus 814. Na2SO4, we just multiply by 1, which leaves us with the minus 1,387. Sorry about that, there wasn't enough room there. And for H2O, we're going to multiply it by 2 because the coefficient is a 2. And whenever we do that, so minus 286 times 2, we get minus 572. Next, we're going to take all of our reactants and add those together. So I'm going to take that minus 940 plus a negative 814. When I plug that into my calculator, I get minus 1,754. I'm going to do the same thing with my products. So I'm going to take that minus 1,387 plus a negative 572. And when I plug that into my calculator, I get a negative 1,959. And then my last step, I'm going to take my products minus my reactants. So I'm going to do my minus 1,959 minus a negative 1,754. This is where you got to be careful with those signs because there is a double negative there. So you don't want to forget one of them because then you'll get the wrong answer. But we end up with minus 209 as our value for delta H. And that would be our answer here. And because it's negative, we could say it's exothermic. Very cool. And we're going to go ahead and skip this one for now. So go ahead and cross that out in your packet. Angrily scribble over it if you need to. I completely understand. Work time. This was in class, people. I mean, if you want to pause now, you can work on problems 6 through 10 in the packet. It's just like that one we just did, or you can continue watching and just knock those notes out right away. But before we get to entropy, we need to understand what a spontaneous reaction is. So a spontaneous reaction is something that's going to occur on its own. It doesn't need anything to sort of push it forward. We also say that if a forward reaction is not spontaneous, then the reverse reaction will be. You don't really need to worry about that right now. We didn't really talk about that. We talked about it a little bit in class if you were here, but the sake of this test, it's not really going to be on there. All you need to know is that spontaneous reaction happens naturally. Non-spontaneous reactions can happen. We just have to put energy into them. And why? What does spontaneity have to do with this? Well, the one way we can measure spontaneity, and I'll tell you how this measures it later, but we use this idea called entropy, which we use a capital S for, which makes no sense. Why S? I have no idea. It's stupid. It was probably some old dead white guy. Who knows? But anyway, what entropy is it's the tendency for all things in the universe to spread out or to become more disordered. So more entropy means more disorder. Less entropy means more order. So like high schoolers, you have a lot of entropy, you're disordered and you're chaos. Mr. C, on the other hand, not today, my desk is a mess, but usually I have a low entropy level because things are usually where they're supposed to be. The way that entropy sort of plays into this idea of spontaneity is the second law of thermodynamics states that entropy has to spontaneously increase. So entropy is always increasing. So any reaction that increases disorder or anything that makes things more disorder is going to be spontaneous. It just happens. The universe wants things to be crazy. It doesn't want things to be neat and ordered. It wants things to go wild. It wants to spread out. It wants to be away from things. It doesn't want to be confined. And whenever we measure entropy, it's going to be in joules per Kelvin. Remember that Kelvin is a way to measure temperature, and that's going to become a little important later on. Anytime we have a positive delta S value, that means that entropy is increasing. So whenever entropy increases, it's going to be delta S, which results in a spontaneous reaction because increasing entropy is good. It's what we want, and anything that we want is spontaneous. A negative entropy or negative delta S means that our entropy is decreasing. Which means there's going to be less disorder. Things are becoming more ordered. That's not good. That's not natural. So that becomes a non-spontaneous process. When we do entropy in this class, we're not going to be sort of studying like how to calculate it. We're going to be more just sort of comparing entropies. Whenever we're comparing entropies, we're going to be comparing them between solid, liquid, and gas. So solids have the least amount of entropy. They're the least disordered. They're very ordered, and we can see that in this picture here of solids. I mean, those molecules, they're not moving. They can't move. They're next to each other. They're stacked up. They're in neat rows. They're perfect. Everything is good. It's like a well-organized desk drawer. No entropy there. Next, we come liquids. Liquids are still sort of confined to the space. They still have to touch each other. They're still compacted and close by. However, they're free to move around. Like within a solid, like whatever molecules you're next to for life. Liquids, on the other hand, they're free to roam. They can go wherever they want. They can be with whoever they want as long as they're, in the same container, they're good to go. So they have more freedom, more movement, which means more entropy. And then last but not least, it's actually double. We have double of our signs here. And that's because gases have so much more entropy compared to liquids. And that's because gases, they're sort of like, they're free. They're completely free. They can do whatever they want. They can move wherever they want. They don't have to be touching people. They can spread out, and they do spread out. They don't like to be next to each other. And because of that, we say that they have a very high entropy. So solids have the least, then liquids, and then gases are over here that they have the most. And the way that this becomes important, because how we determine whether or not a chemical reaction increases or decreases in entropy is we have to look at all the sides and see like which side has more gases and which side has more solids. Whichever side has more solids is going to be the side with less entropy. Whichever side has more gases is going to be the side with more entropy. So if our products have the side with more entropy, we say entropy is increasing, which means delta S is positive. If our reactants have more entropy, though, we would say that entropy is decreasing, which means delta S would be negative. This whole thing just sort of goes through what I was talking about how they were like ordered and stuff. Entropy is temperature dependent. That's why its unit is joule per Kelvin. It does have something to do with temperature. And the way that it works basically is that the more temperature you have, the more entropy you're going to have. The hotter you get something, the more disordered it's going to become. And that makes sense. If we start heating up an ice cube, it's eventually going to melt. So it's going to go from a solid to a liquid. And we know that liquids have more disorder than solids. And then eventually, if you heat it up more, it'll turn into a gas, which once again, gases have even more entropy than liquids do. So as we add temperature, entropy is going to increase. This is pretty much the gist of a problem for entropy, or a big problem for entropy, is we're going to be asked to predict what delta S is. And when we do this, we have to look at which side has more entropy, which means we're looking at the state symbols there. So if we look at this reactant, our reactants have one solid. Our products, on the other hand, have one gas and two liquids. We know that solids have the least amount of entropy, and gases and liquids have the most amount of entropy. So because our reactant side only has a solid, this has the less entropy side, so this is less, and this is our more entropy side. So we're going to go ahead and say that entropy is increasing. So we're going to increase that delta S, and because we increase delta S, that means delta S is going to be a positive number. And that would be basically what our answer is. We would just say, well, our prediction is delta S is positive. And if we wanted to provide a reasoning, we would just say, oh, because the products have more gases and liquids than the reactants do. So now that's all the notes for today. We just have one more topic after this. After doing this, you can now work on problems 11 through 14 in our packet, which are just like the ones above. So you can now, if you want to do all of them, you can work through problem 14. So 1 through 14 is everything that we've covered so far. So work on that packet. If you have any questions, let me know. I'd be more than happy to help you out. And happy chemistry.